Hi, everybody. So I'm Lian Keqing, and I'm with Yiwei Zhang. Our group is working on the FastThread group project. So it's a multi-core processor era, right? So multi-threading programming is becoming more and more important because there are several advantages. First is it can allow us to better utilize multi-core processor. Second, we can do some resource sharing between multi-threads via shared memory or message passing. Also, threads are more lightweighted than process creation and context switch. For example, so this is a screenshot of my computer. So usually on our machine, there are possibly hundreds, even thousands of threads running, and context switch or thread creation can happen every time. So our project goal is to enable faster thread creation and thread context switch. Usually for short-lived thread, for example, web request, which is sub-milliseconds, and if the thread creation or context switch overhead is relatively high, maybe the overhead is even longer than the thread execution time. And after millions of web request accumulation, the overhead is unbearable. Also, there are a more lightweighted abstraction named fiber. So compared with fiber, thread is usually preemptive scheduled by the kernel, and fiber is implemented in this user space, so it's cooperatively scheduled. For example, a fiber can yield itself actively and handle the control to another fiber. So in such circumstances, the scheduling mechanism can be handled back to the user, and maybe they can just implement some better scheduling mechanism. But because fiber is implemented in user space, so fiber cannot support privileged operations. And if fiber is not carefully used, the scheduling could be even worse than the kernel default scheduler. We have done some benchmarking in our first half quarter. There are some statistics. For example, the thread creation is usually much longer than the thread fork. And also there are context switch, and also we have tested some task creation and fiber creation, and you can just take them as an example. And all these benchmarking are were run in QEMU virtualizer, and we use RDTSC, the read timestamp counter function, to benchmark these CPU circles.
This is our work after the midterm. So this involves measuring context switch profiling, measure thread creation profiling, and then finally optimize thread creation. So let me first talk about context switch profiling. This involves five main steps, which is critical section protection. This step involves like grab a local lock and disable interrupt, costs about 500 cycles. Second step is get current thread / scheduler info, which is pretty light. The third step is the CPU do a rescheduling pass, choose the next thread to run on that CPU. The fourth step is do the actual context switching on that CPU. The cycles are not determined yet because we will talk about in the next several slides. The last step is exit critical sections and restore all the states. So here are some challenges we have been facing for measuring context switch. The first reason is because booting the kernel itself will trigger many context switches, will trigger many threads and context switches. The second one is typing in the command line will trigger also many context switches because our testing code is should be triggered by benchmark command. The third reason is when the CPU is switched from and when when the thread is switched from and when the thread is switched to on the CPU, this timestamp is not is kind of not in the same timestamp. These information are all stored in the thread's local stack, but not global in the sense of the kernel. So we have a mismatched timestamp problem. The last one is because there are just so many context switches between threads so that we cannot get a very clear sense of what's the average time for the context switch. So in order to solve all of these problems, we developed several approaches. The first one is to differentiate the context switch function call triggered by our testing code versus the rest of the kernel code. So we pass in a flag which is true only in the case that this context switch is called in our testing code. And the second step is to measure context switch for n yields and divide it by 2n. This will ignore a lot of printing messages in a single context switch, but instead sum it up in one single pass so that we can disable many prints and get a better sense of what's the average time for the context switch. The third approach is to store all different kind of profiling time in a single struct, so we can know what's the time cost in different steps for a single pass. The fourth step we have not implemented yet, but we should store the time on the CPU instead of on the thread stack. So like when the thread is actually doing a context switch, we should get the time by calling rdtsc, store that time on the CPU. And when the CPU is doing the rescheduling, it will switch another thread. When the thread B is switched back to that CPU, we will get the time on that CPU and calling the rdtsc.end so that we can know what's the time for the CPU to do a context switch. This is a snapshot of our testing code for context switch. As you can see on the left-hand side, this is the handler. On the right-hand side is the testing code for main function. So we have implemented a barrier so that would enable two threads to kind of start on the same point and avoid the cases where one thread is not ready, but another thread is already starting to run. So after the barrier stuff, we call the yield 100 times for two threads, so that this will cause 200 years for a single pass. We sum those different time up and then finally divide it by 200. That's our average time for context switch. However, there are some abnormal observations. The first one is context switch measurement is still waiting to be fixed. And the second one is we find out that adding extra profiling time to the context switch source code would introduce overhead to the context switch function in general. So before, originally, without the profiling time, it's only about 5,000 cycles, but after it will rise up to 10,000 cycles.
We have also done detailed profiling on thread creation. We split thread creation into 4 phases. So first, we want to try to reanimate a dead thread body, and this phase ranges from like 7,000 to 400 million thousand circles, and it keeps growing as the number of thread creation and join increases. Just like the computer, when the computer is on, the number of threads started and ended will keep growing, and we will talk about it more detailed. And the second one is we have to make our own thread. We allocate the stack space. We set some parameters, and this phase will cost like 80,000 CPU circles, and it's very stable. The third one is we have to initialize the thread we create, and it usually costs 250,000 CPU circles, and it's also stable. Lastly, we have to move our thread to the kernel scheduler, and this one is the overhead is very small. It usually ranges from like 6,000 to 17,000 CPU circles. And according to Amdahl's law, we want to optimize this thread initialization and the thread reanimation part. So let's take a deeper look on the nkthread init function first. It basically initializes some parameters like the stack pointers, some CPU registers, and the reference count, and the thread parent, and where it is its placement CPU, something like that. And also there are 3 main functions it called. They are NK schedule thread state init, nkgc thread state init, and nkwait create. And after we take a deeper look on these 3 functions, we find it difficult to optimize them. So then we take a deeper look on the thread reanimation code. So why this thread reanimation keeps growing and it's very slow in the end? This is the core code in the thread reanimation. So in Nautilus design, there is a global scheduler state which contains a global thread list. And when we do a thread reanimation, we will acquire the header of this thread list, and we keep doing linear search over the list, and we try to find something satisfying all the conditions, like the thread status is reapable and the thread has been exited. Also, the thread reference count is 0, and the thread body stack size should be larger than our requirement. Also, the dead thread body, its placement CPU should be equal to our requirement. Then we finally found the target as reanimation. So it's clear that when we create and join threads the global thread list will keep growing, and the average linear search time will also keep growing. So we have some simple optimization idea. For example, we can have a per CPU thread list maintains, and also we can keep these thread list sorted. For example, we can sort them according to their stack size, and then we can improve our thread reanimation linear search time. This is a comparison over the old mechanism and our new fast thread reanimation search. As you can see, if we try to create and join threads until 500, the average CPU cycle cost for CPU reanimation part has been reduced for more than 50%, and it's very significant. For our future work, we want to, maybe we can maintain a more fine-grained thread list for even fast thread reanimation. For example, we are doing linear search, and maybe we can have something like hash table to further improve the thread reanimation. But it's also a trade-off, because if we want to maintain a more fine-grained thread list, then during some other functions, you have to manipulate these containers very carefully, and this will increase the overhead of some other functions. So we need to do some trade-off. Also, eWay will fix the context switch measurement later. And that's all. If you have some questions, you can just comment on our video, and we will respond. Thank you.